Hello everyone, welcome back. So today is the second day of third week of this lecture series. So we were finding the similarity between a group multiplication table which was formed out of just an abstract group, and we were comparing within a particular group multiplication table which was formed for ammonia in particular. Which belongs to C3b point group. So we figured out that when we compared both these group multiplication tables, that all the elements in that multiplication table, they have a one-to-one correspondence. So that means the elements of the group itself, that is the group that had like E, A, B, C, D, E, so F, and our C3b point group. So all the elements had one-to-one correspondence, and we also looked at what are the actual correspondence. Okay, so which one is which. Now the groups which have one-to-one correspondence, they are called isomorphic to each other. Okay, so these G6 and C3b point group, they are isomorphous. Okay, and if there is more than one-to-one correspondence between two groups, they are said to be homomorphic to each other. Okay, and all groups are homomorphic with the group E. Obviously, that is not a thing to be surprised of. So where A is E, or B is E, or C is E, any element that you can think of will have a corresponding correspondence with the identity element for that particular group. Okay, so now let us have a look at another interesting aspect of this symmetry elements belonging to a group. We have formed a group from the symmetry operations of the molecule that is under consideration. Now we can further classify certain operations in that particular point group under something called class. So what is that class? We will know in a moment. So before we can talk about what is a class, we should know something called similarity transformation. So what is similarity transformation? So if you pay a little attention to the screen, you will see what is the definition of similarity transformation. So suppose you have A, B and X as elements of a particular group, and if the this term X inverse AX is equals to B, which is also another element of the group, then we say that B is the similarity transform of A by X. Okay, so similarly, if we have something like another element Y belonging to that group, such that Y inverse B Y equals to A, then again B and A are the similarity transform of each other. Now when two elements belonging to a group are related through a similarity transformation, then we call those two elements are as the conjugate of each other. So here particularly A and B are conjugate of each other because they are related through similarity transformation. Now there are certain properties of this conjugate elements that we will be looking at next. So the first property that we will look at is here, that is all the elements are conjugate with itself. Okay, so what does it mean? So we showed that X inverse AX can be some element B. Now what this particular property that we are talking about says is that for any element A and X belonging to a particular group, then no matter what, this will always be there. Okay, that is a trivial case. Now that means any element is a conjugate of itself. because earlier we were dealing with x inverse A x equals to B, and we said that there's B and A, they are conjugate of each other, and if I can have this relation, that means that A is a conjugate to itself. Okay. Now how do we prove that? That is very easily, it can be proved very easily. So if I say write in this way, now if I can multiply this quantity by its own inverse, that is A inverse, then what we have for here A inverse A means identity. So that means A inverse x inverse for this part A x. Fine. Now what does this term mean? So in order to find out, we can utilize another property of the elements of a particular group, which says that reciprocal of or say if I say in this way that reciprocal of a product of two or more elements of a group is the product of the reciprocals of those particular elements, but in reverse order. What does it mean mathematically is following, that if A, B and C are member of a group, then A, suppose I define a particular binary operation, then this is equals to C inverse B inverse A inverse. Okay. So this is a property of the elements of a group. Okay. And this also can be very easily proved, like if I start with say A, B, C, I am not writing the stars anymore, but this is implied, and if I write A, B, C equals to D, and then if I multiply both the sides by this quantity, so what we have? We have C inverse B inverse A inverse followed by A, B and C equals to C inverse B inverse A inverse, right? Now A inverse A is identity. So identity when it's operating on this B and C, it gives B and C. So then next I have B inverse B C. So B and B inverse and B will give again identity, and we are left with C inverse. So that will also ultimately give identity. So ultimately what I have is identity equals to D. Okay. So that means C inverse B inverse A inverse D. Now what does it mean? That this quantity, when it is operating on D, it gives me identity. That means D is the inverse of this, correct? So in other words, I can write D is the inverse of this one. So I can write like D inverse equals to this. So D inverse means this ABC is D. So that means I have A, B, C inverse equals to C inverse, B inverse, D inverse. That's what we started, we wanted to prove, right? So the reciprocal of the products of two or more elements of the group is equals to the product of the reciprocals in a reverse order. So now, knowing this one, what can I write for this? So this is A inverse X inverse. Fine. Suppose if I can separate this two. So this means X A whole inverse and then A X, correct? So this is equals to identity. Now this is only possible when this X and A commute. Okay. So then only if it commutes, then I can write it's like X A, correct? So in that case, obviously I have this one. So one element for A, I can always have like E, identity. Okay. But other than identity, other than this trivial solution, I can find particular element which will be commuting with this A. Fine. So suppose that is B. So then B A B is equals to E. So what does that mean? That ultimately this comes from this expression. Okay. So if this is valid, then and that is valid for some x which is which commute with A, right? Which is obviously possible, and therefore this is valid. So in general, what we have is any element is conjugate to itself. Okay. Now there is another property of this conjugate elements, that is if A is conjugate to B, then B is conjugate to A. Okay. That can also be very easily proven. So what it says here, that if A equals to x inverse B x and B equals to y inverse A y in that group, then this is valid. Okay. This also can be very easily proven. Say for example, you have this, you start with A equals to x inverse B x, and you multiply in a way. Let me show you that. So we start with A equals to x inverse B x. So here A and B are conjugate. So that means B and A are also conjugate. So B is also conjugate to A. Now how do I prove that? So what I can do, I can left multiply this A and this side also by x, and right multiply with x inverse. So let's do that. So what do we have here? This part will give identity, and this part also will give me identity. So ultimately I have B here, right? Now in this group every element will have its own unique inverse. So there will be some element y which is the inverse of x, correct? And then therefore y inverse will be x. So then what I can write for this part, that is B equals to y inverse A y. Okay. So then according to the law of similarity transformation, B and A are conjugate again. So we have seen that if A is conjugate to B, then B is also conjugate to A. And thirdly, if A is conjugate to B and C both together, then B and C are also conjugate. So that also can be very easily proven in the same way, and I will leave it to you. So you try it out and you prove this. Now if you take any particular group and then you perform similarity transformation on all the elements, then if you find a set which has to be a complete set, so if you find the complete set of elements which are symmetry operations here in case of point group which are conjugate to each other, then that complete set is called a class. Okay. So this has a tremendous importance on in the applications that we are going to have in a few more classes later. Okay. So you should understand what is class, how it is formed very well. So in order to form a class, I mean one can easily verify this statement here, that the orders of all classes must be integral factors of the order of the group. So similar to the subgroup, here the order of order of any class will be integral factor of the order of the group. Okay. Now with this knowledge, let's try to find out the classes which are present in case of G6. So how do we find out the classes? The answer is very simple. We have seen that we know the definition of class, that is the complete set of conjugate elements. Conjugate elements are found by doing similarity transformation. So what I am supposed to do here, you have in G6 you have 6 elements. Okay, so choose any particular element first, then perform the similarity transformation using all the elements present. Okay, so for example, here you have suppose you start with the element E. So what you do is following. So what you do is you take E and then keep doing the similarity transformation using all the elements that are present in this group. So you get one answer here. Okay, then you do say A inverse E A, you get another one, then B inverse E B, and you keep doing until you reach the last element of the group. And then whatever the results that you get, that you will get 6 data, right? So 6 elements you will get out of this simulated operations, because you will do another 3. Now out of this 6 you may have 3 different elements appearing say twice, or you may have 2 different elements appearing thrice. Okay, so those 2 or 3 elements that you find which are coming again and again, that will form a class, and that's what exactly we are going to do. So first what you have to find out, we will do this job for E, and you get that whatever you do, no matter what element that you are using to do this similarity transform on E, you will get back E only. That means that identity is it forms a class by itself. Okay, that is the term that we will use. So identity forms a class by itself. So there are no other element in that class that identity alone forms. Now what are the other classes in G6? So you can you can do the similarity transformation on any other element. Say for example, you start with this element A, and what you get here is written. So on A, if you do the similarity transformation, you get A twice, B twice, C twice. So that means A, B and C, they are conjugate to each other, and A, B and C form a class whose order is 3. So we have a class of order 3, right? And if we, so here one thing I should mention, that once you have started operating doing the similarity transformation on one particular element, and after this exhaustive similarity operations on that particular element, you generate certain set of element. In the next similarity transformation that you would like to do, because you have got only 3 elements in this class and identity, so there are 2 more elements which are still left, and you would like to find out whether they form a class or not. So in that case, you start with one of them. Okay, if you do a similarity transformation of any one of them, you are going to get back A, B and C, which you have already found, right? So there is no point of doing repeating the same thing. So you do it with say D. You could choose F as well. Okay, both of them will give you same result. So when you do the similarity transformation on D in the same manner, you find that D and F, they are repeated 3 times. So what you have essentially, that they form a class, because D and F are conjugate, and the order of this class is 2. Okay. Now this example was shown on an abstract group. Now in case of point group, this is an really important thing, and so we need to find out the classes in case of symmetry point groups as well. So you can actually test all the possible symmetry transformations like you did earlier, and find out the conjugate elements. So if you have very large group, then obviously this is a tedious process to find out the classes. But once you have found out one particular class by similarity transformation, then your job becomes a bit more easier with every class that you find out. Okay. Now let's try to find out the certain general rules in regarding the classes and the relation between particular symmetry operations and the kind of class that they will form. So one, we have already seen using that abstract group that identity forms a class by itself. There are certain other symmetry operations which are the elements of the point group. They can also form class by themselves. One example is identity we have already stated, and inverse and sigma H plane. Okay, it's not that any sigma. We will take an example later, and we can see that this is valid. But whenever you have a sigma H, it always forms a class by itself, and so does the inversion center. Again, any proper axis of symmetry, and if you generate the symmetry operations from that, then generally this Cnk and Cnk inverse, that is Cn minus k, they are in the same class. Okay. For each value of k, as long as there is a plane of symmetry along the Cnk axis or a perpendicular C2 to Cnk. So this is a generalized thing. So if you try out for certain point groups, then you will appreciate this general rule, and next time onwards, whenever you look at any particular point group, you do not have to do the similarity transformation all the time, because these are certain general rules that actually have been found by extensive amount of similarity transformations on a variety of point groups. So this is an acquired knowledge, and you can verify yourself, and then you can actually get rid of doing all the tedious similarity transformation in order to find a class. And similarly, you have like sigma prime and sigma double prime are in the same class when if there is an operation which moves one plane into other. Here probably something that you already know. We mentioned about the equivalent symmetry operations, right? See here exactly that's what gives you that sigma prime is a particular sigma plane. Say suppose a sigma v. Let's take an example, ammonia. Okay, so we have 3 sigma v's. You start on one sigma v, you apply C3. So this sigma v gets transformed into sigma v prime, and then it transforms into another sigma v. Okay, so these 3 sigma v's are equivalent. So here exactly this is being said that if you can move one of this plane into other by another symmetry operation, then those sigma planes will form a class. So knowing this, it will be very easy for you to tell that 3 sigmas in C3V point group to which ammonia belongs, they will form a class. So sigma v, sigma v prime, sigma v double prime, if I can name them in that way, then these 3 sigmas will form a class. And if you look at the C3 and C3 square, and if you perform the similarity transformation, you will easily figure out that C3 and C3 square, they form a class by and identity obviously it forms a class by itself. Okay. Now one thing I will mention here, that is suppose I am talking about C3V point group to which ammonia belongs to. So how do I write all the symmetry operations? So I write E C3 C3 to say sigma V prime sigma V double prime sigma V triple prime, like this. Now once I have found out the class, I rewrite this in a way which is C3V E, and I club these two because these two forms class and this 3 form a class. So I write 2C3 and 3 sigma V. There is a specific reason for writing in this way, and there is a specific reason to form a class, because certain properties for those symmetry operations belonging to a class are same. What I mean is, like, any element belonging to the class will have the same property. So we will stop here today, and we'll meet again for the following class. Till then, have a nice time.